The first thing is, anybody have any questions from homework stuff? It's going beautifully. I'd love to see some of it. So, anytime. Okay. So feel free to, come during office hours if you have any trouble with that, and just ask during class. So last time, I think I just barely got into the idea of this new thing. And I really hope I got it through to you guys, why we need an entirely different distribution. Can somebody tell me? Say again?
They're not normally distributed.
To be honest, if n gets big enough, it becomes normal enough. So what's the fundamental reason we need a new distribution to analyze some of the stuff we're going to analyze with chi-squares? Anybody remember? So when I'm looking at means or percentages, they fall into a normal curve, and the shape of that curve is determined by a standard deviation, right? So what we're about to get into could be used to do hypothesis tests. It could be used to do confidence intervals. It could be used to do all this stuff for standard deviations. So now I don't just have one standard deviation, I've got all of the standard deviations. And they end up looking like that thing we looked at last time. Right, so it's been skewed right. And to be really honest, if my degrees of freedom were 1, meaning I only have a sample size of 2, it looks like this, which is exceptionally funky. Okay. All right. So several things I want to do today. One thing, of course, whenever we have a new table, we just do a few problems just getting used to reading the table, right? And then we want to introduce our first, so I don't know if you remember, when we learned normal curves, we got used to the z-table, right, the z-score chart, before we did any real problems. We just looked at some z-scores to make sure we knew how to look stuff up. So basically do the same thing today to start off with. So let me give you, let me give this. This is chi-squared chart, similar to Z and T. So before I put that up there, I want to remind you guys the one formula. So like for z-scores, we've got, here's the main formula we first learned, right? And then we learned many, many, many more. We learned all these different z-score formulas, but they all kind of fell into that shape, depending on the situation, right? So now we've got this shape. We so far have told you one chi-square definition for an equation where if I do this for a sample, I can find where it falls in this picture. Does somebody remember what this was here? That makes sense?
1, 0.
0, I like it, right? Because couldn't you pick a sample? And I asked you this last time. What's the smallest standard deviation you could get from a sample? What's the smallest spread of data that you could get if all the data was what?
0.
No. Well, I mean, sort of, but it doesn't have to be 0. If they're all the exact same number, what's the spread? What's the standard deviation if my data is 5, 5, 5, 5, 5, 5, 5, 5? 0. Is there any spread? No. Do you guys remember how standard deviation is defined? what was the first thing we had to do back in the day? To construct the standard, didn't we have to do this? So if they're all the same number, these are going to be a bunch of zeros. And I don't care what the hell I do after that. When I add them up, it's still going to be 0. Okay. Doesn't that make sense? If I have a number that represents the spread of data, and I have data that are all the same number, the freaking spread better be 0, or else it doesn't make sense, right? It may be. So that's why this starts at 0. That's the lowest that I could get here. But then I can get stupid, crazy standard deviations. I mean, if I just pick a random sample, I could get, you know, if it's ages, I can get somebody who's just born. I can get somebody up to who's 120. I mean, I can get insane spreads. So that's why theoretically this just goes forever. Okay, I like it. Enjoy it. Appreciate it. Okay. So, I'm still going to have degrees of freedom, which somebody beautifully caught from right here. I appreciated that when that happened. The degrees of freedom will not always be this, though. It could change depending on the situation. So the very first thing we're going to do is funnily, doesn't sound right. Crazily enough, is not going to use this equation, and we're not going to use this definition of degrees of freedom. Yay! But to me, I like to start here. I can do things like 0, we know what that means. Goes really big, we understand why. Shouldn't most samples have standard deviations close to sigma? Yes? If I take a nice random sample, shouldn't I expect to get something close to this? And that's why there's such a nice peak right here. Right? And in fact, the tallest point is close to n minus 1. The mean actually is the degrees of freedom. All right, enough of that. Okay. So how does this chart work? This is B. No. You've chosen poorly, Jeff. There we go. So if I had, for example, there you go. A sample, let's see where I'm going to borrow. It's a paper. There. All right. Okay, so one thing to notice, one really strange thing about this. Remind me on the z-score chart, when you look up a z-score, it gives you the area where? Remember, when you look at the z-score chart, the z-score chart, it gives you the area below, to the left. What does this chart do?
Right.
Yeah, we really did that just to screw students over. Now, so that's the first thing to notice. So, for example, let's say I have a sample of size 2. Let's start with something. And we're doing a situation where the degrees of freedom is exactly what you would expect. All right, and let's say that I want there to be 0.05 to the right. So it would look like that, right? Can you find that chi-square score? What do you guys got?
Is it 3.841?
Yeah, 3.841. remember that one definition of this is this. So the probability that I would pick a sample of size 2 where the standard deviation I get, when I square it and I divide it by the variance, I get 3.841. That's got a 5% chance of happening. Let me say that again. There's a 5% chance that I would pick a sample whose variance is almost 4 times the variance of the whole population. Let me say that one more time. There's a 5% chance that I would pick a sample whose variance is way bigger than the actual population variance. Almost 4 times as big. You guys, shouldn't that be kind of on the less likely side? Yes?
Say that one more time?
Yes. There's a 5% chance that I would pick a sample whose variance is almost 4 times as big as the variance of the population. Because again, what is this again? What is this? What is this? Where did we just find this? Where did we just find it? What chart is this? No. This is the area. What is this? This can't be an area. It's bigger than 1. What did we just look up? What chart is this? Chi-square chart. So what did we find? 3.841 is a chi-square score. When I look up in the t-score chart, when I look alpha equal to 0.02 or whatever, and whatever tails, and I find a t-score, don't I? Right? Okay, so here I found a chi-square score. So let's just round this to 4 for the sake of discussion, okay? Let's just round it to 4 for right now. So if I put that here, n minus 1 in this case is 1, correct? Doesn't this say that the variance of the sample I get is 4 times as big as the variance of the population? Yes? Yes? Okay. Shouldn't that be on the slightly stranger side to do that? Does that make sense? Shouldn't it be a little weird to get a sample, a nicely picked, beautiful, random sample whose variance is 4 times as big as the actual variance of the population? That should be a little unusual, and sure enough, there's a 5% chance that would happen. I like it. Especially because we've only got samples of size 2, yes? That's crazy. So you'll notice, the bigger our sample gets, the more and more room there is for the standard deviation to get crazy big. That's why the numbers get bigger as I go down. That's one reason why it is. Okay. All right. So, what if I wanted, let's try another one. What if I had n equal to 7, and I needed to find 0.05 there. I want the chi-square score for that. This is a lot like when we first learned how to use the z-score chart. Is the area in the right place for the chart to understand? No. Nope. Because this chart wants areas to the right, because stats people are evil. You know, you're used to things left, so we went, let's go right this time. So, how much area is to the right then?
95.
0.95, I love it. And of course, what I have to do with this?
Minus 1.
Good. So now I can look at 6 degrees of freedom, and I want 0.95 to the right, 0.95. So I get 1.635. different. The concept is different. They put the area in the wrong side of the thing related to what we're used to, but it is similar enough that this shouldn't be like a complete shock to find these things. What's really weird, what's really weird is there's not negatives and positives, it's not symmetric, right? So we used to be able to find a two-tailed thing, we found a t-score of 1.99, this would be negative 1.99, bam! You ain't got that shit here. Nothing goes below 0, it's not symmetric. Okay. Let me see what you guys think about this. What if, running out of paper, what if I wanted to make a 99% confidence interval for standard deviations? And let's say my sample size is 11. Can you figure out what these two would be? I would call this chi-square small, and I call this chi-square big. That's what I normally call those. Can you figure out what those would be? Of course, what area do you need to feed the chart for it to tell you the chi-square you want? You need the area that is
To the right.
to the right of whatever chi-square you want, correct? Pick one of the two chi-squares I put up there.
Small.
Okay, do this yourself.
Oh.
What area is to the right of it? Look it up. Don't forget degrees of freedom thing, right? Do it. If you don't know what to do, draw a little duck or something. Don't just stare at me or the wall or something. Preferably don't draw a duck. Preferably try to do it because I'm not grading you. Might as well make a mistake now. Get it out of your system. All right. What's the degrees of freedom? 10. If I look at chi-square small, let's look at chi-square big first. What area is to the right of it? We've done this kind of thing before. There's 99% inside, how much is outside?
2.558.
Don't give me the chi-square, I want to know what the area is.
Would it be 0.01 or 0.005?
Yeah, 0.01 total outside, so 0.005 on this side. Now, real quick, I don't know if anybody's concerned about this. It's not symmetric, but when we do confidence intervals, we would chop it in a way that the areas are equal. The shapes aren't equal, but the areas are equal. Okay. So let's see. So now we know 0.005, 10 degrees of freedom. 0.005, 10 degrees of freedom. So it looks to be 25.188, right? Is that cool? Okay, and then this guy, what's really funny, let's do this one and then I'll show you something kind of nifty. So real quick, does anybody know what this area is to the right all the way? This is 99, and this is 0.5%, right? So of course, what area is totally to the right of this? 0.995. Yes, is that right? Okay. This isn't groundbreaking stuff. We're just doing 1 minus something or other. And adding it on top of this. So now I've got 0.995. So notice this. Don't you guys see how this sort of breaks it up? So if I was doing a confidence interval, that I've used, these kind of go together. These go together. These go together. So this and this go together. So it's kind of nice how the symmetry if I step in, I'm getting smaller and smaller confidence levels. You guys understand what I'm saying? So this goes with this, and then you can step in, you can step in. Okay, it's kind of nice. So now I'm looking at 0.995, 10 degrees of freedom. I think this is the one you were telling me about a second ago, 2.156. Okay, and then I would do weird shit with that to get a confidence interval. Okay. That is equivalent to finding the t-scores for a confidence interval. It's the same conceptual step. Okay, maybe. All right, so let's keep this here. We're going to use it in a minute. So now that we sort of see how this thing works, plus just to point this out in case. Let's see, how much do I want to do this? What's another reason why these get bigger and bigger and bigger is because doesn't the chi-square have this piece in it? So as my degrees of freedom get larger, I keep multiplying by more and more and more here. So that's another reason why these are getting so crazy. Look how big they freaking get. We are not used to that. The chi-square is a different beast than T and Z. All right, so here's the chart. We talked about the nuts and bolts of how to freaking read the chart. Now we're going to look at a type of problem that uses chi-square stuff. So we got to figure out why it makes sense. Hold on. Turn that dude around. Use the remote control.
Turn.
Alright. So, as I said, the first problem we're going to do is not going to use this. That is sort of like the main z-score formula. So we're going to use another formula for chi-square. The idea is when I calculate it, the number I get, the chi-square, does fall into that shape. So there are multiple formulas that kind of fall into that shape. We saw that for z-scores, right? So we already are used to this idea. So what we're going to do, we're going to build this formula. And the way we're going to do it, okay. Let's say that as a teacher, let's say that I looked at all of the 160 courses for the last 10 years, and I found this distribution of grades. So I found that 10% of the students ended up with an A, 25% with a B, 35% with a C, 10, I think, no, oh shit, 20% with a D, and then 10% with an F. Did I actually do this? No. This is sort of roughly based on, yes, it is sort of roughly based on what I would expect. But anyway. Does this do the right thing, by the way? Can somebody double check? Yes, okay, I think it does. What is it supposed to do, of course? It better freaking add to 100% or else Jeff made some weird shit happen. So, what if I take a sample of this semester's students and I say, I think this semester's students, I think the sample shows that this semester's students are doing better than the last 10 years. Are you guys, that claim by itself makes sense, right? So if the claim is, I think that all the stat students this semester are doing better then what would be predicted from the last 10 years worth of data? That claim makes sense. We currently, right now, have no freaking way to do that at all. We have no way to do that. What kind of claim can we handle? I think the percentage is more than 20%. We can handle that. How many percentages are up there? There's several, yes? There's not just one. So I can't just do a straight up hypothesis test and be thankful for this. This is not a hypothesis test we're going to do. It's got some similarities, but it's not the whole steps. So, how do you think, I kind of gave it away a second ago, but how would I start to investigate my claim? What would I have to do? If I want to investigate my claim, what would I do? I think that stat students this semester are doing better.
Make a claim.
Second,
Make a claim?
that's the claim. I already made a claim. What do I do to test it?
Get the grades of current students.
Yes! So get a sample of grades, right? So let's say I take a sample of, all right, this is more, let's say I'm doing it of more than just Grossmont I've known, because we're going to do 400 students. I don't think we quite have 400, but if I, can you tell me, before I even take the sample, can somebody tell me how many A's I expect to see given what I've seen over the last 10 years?
40.
Okay, so let's make an expected column here. So I expect to see 10% of 400 is 40. Is everybody cool with that? And I expect to see 25% of 400 is what? Thank you. 25% is 1/4. 1/4 of 400, 100. 35% is easy, watch. 10% plus 25% is 35%, so therefore 40 plus 100, 140. Yay! Percentages kick ass. And then 20% is twice 10%, so it's 80. And then 10% I already did. Yay! Now what can I do to make sure I did all that right? What should happen with those new numbers now? Should be freaking adding up to 400. I don't want to lose anybody on the way. Thankfully, if you add them up, they do add up to be 400. So this is what we would expect to see. Have I actually looked at any data yet? No. Besides this, but I haven't looked at any data currently. This is what I expect to see if this trend is perfectly holding, right? So let's say I observe this. Here's my observations. What'd you make of here, Jeff? Anybody have any immediate reaction to that? Does it look roughly the same? Where are the main differences there? So here's my sample of 400 students, right? What are the main differences?
In F, it's a lot lower.
Which ones? Yeah, F's a lot lower. What are the higher grades?
A, B, C.
All the passing stuff. With the less grades are the failing stuff. So it does look like that they're doing better. Remind me why I can't just stop, because look, they're doing better with the shit. Why can't you just stop right there and say, there you go? Why do any more, Jeff? We can see it. They're doing better. Same thing with hypothesis tests, remember? There was a point we couldn't stop. We had to do all the steps. We couldn't just go, well, look, it's better. What the hell? Why?
This
One-
might not be so better that means that it actually is.
Okay, good. But there's one key word I want to hear.
It's just a sample.
Just a sample, there it is, okay. Or phrase I would take. It's just a sample. So, putting that together, what you said, Audrey, since it's just a sample, not only does it have to be different, it has to be different enough. Right? It's got to. So somewhere we're going to set up a benchmark where evidence is going to start, and then we're going to see if we made it in there, if we made it far enough away. So, considering what we're trying to do here, we basically really just did the next step. What should the next step, the immediate next step be if I'm trying to see if this is different from this? What should I do with all the numbers? What's the immediate thing that makes sense?
Convert them to percentages.
Nope.
Okay.
Subtract them, yes? Isn't that how it's two more, so it's, right, maybe? So, alright, to be honest, this doesn't really matter, but we do observed minus expected. And just to cut to the chase, you guys remember, this might be out of your mind, you might guard yourself from past trauma, but do you remember standard deviations and we had to do x minus x bar squared because of stupid negatives? Does anyone remember that? Some negatives came out, we had to kill them. So we're going to square this. Okay. For the same reason, right? So let's see what we get. This will be 2 squared is 4, right? The difference is 11 squared, 121, yes. The difference is 3 squared is 9. The difference is 4 squared is 16. It's actually negative 4, but who gives a shit? I'm squaring it. And then here's 12 squared is 144. Okay, now. So this next step, let me ask you this. If I had $3 more than you, when would that be a huge deal? If I had $3 more than you've got, when would that be a huge deal?
If I need $3.
Okay, if you need $3. What if all you had was a dime to your name, and I've got $3 more than you? That's huge, isn't it? Relatively, that's a huge difference, yes? I mean, when I was 6, and if I got a quarter from the tooth fairy and the neighbor got $3.25, what the shit? Are you guys with me? Holy shit. This guy next door could buy some, what was better about his tooth? What the hell? Right? And of course now I know it's, my parents were not as well off, so oh well. Oh. Sorry, spoiler alert, there's no tooth fairy. So what I'm trying to get at is, if I have $1 billion and you have $3 more, who gives a shit, right? But if I have 10 cents to my name and you have $3 more than I do, that's huge. So this next step hopefully makes sense then. Not only am I curious about what the differences are, I'm curious about how relatively big these differences are. So what we do is we take what we just did and we divide it by the expected. Just to get an idea of how relatively big the differences are. So this will be nice and easy right here. 4 over 40 is 0.1. Is that cool? You guys can help me out. This is easy. 121 divided by 100 is 1.21. Yes? Nine divided by 140 is something. That much I know. Is it 0.06? Probably not, Jeff. Close. I think it's close. Is it 1, 2, 1, 2, 4, 2, 8? 0.063. No, it's good. You guys get that? Anybody? Is everybody with me what I'm doing? 9 divided by 140?
0.064.
0.064? And then 16 divided by 80. Pretty sure that's 0.2. Is it 0.2? Yes. And then 144 divided by 40.
3.6.
3.6. Okay, now, let me stop for a minute. Not talking about chi-square shit yet. Does every step we took make some kind of logical sense? I mean, considering what we're trying to do, the fundamental thing we're trying to do is to see if what we saw is different from what we expected to see. All right, well, I'll take it the freaking difference. The square shit should be old news to us, right? Squaring, because some of it's negative, that's going to screw us up if we don't square it. Plus, it's part of the reason why it's chi-squared. They're normally made up of sums of squared shit. And I just gave away how the chi-square comes into play. Chi-square is fundamentally the sum of squared, I don't want to say this, data points. So each of these are data points, so I'm going to sum up all of these things. Somebody help me out. What do you get when you add these up?
Yeah.
Is it?
Yeah.
Dude,
Hoorah.
I appreciate the surprise telling me before. Sorry. All right. Relative to a lot of stuff we've done in this class, is this difficult? No. Here is the formula right here. I kind of buried the lead here. This is the alternate formula, or one of several alternate formulas for chi-squared, just like Z has alternate formulas for it. Same thing. This is sort of like, I don't want to call it chi-square star, but it's sort of like Z star, because where did it come from? Didn't it come from our sample? Okay, so now I got to go back. So, what I didn't give us yet, because I wasn't worried about it yet, was, oh boy. If I zoom out too much, I'm not going to be able to see shit. I'm going to go over here. That is like Z star. So what we need to do now is, they need to tell us what level of significance to do this at. So let's say that they give us alpha is point, doesn't matter, let's just do 0.5. And here is the other thing. Good, this is called, I might as well tell you what this is called. This whole thing we're doing is called the goodness, yes, the goodness of fit. Yes, that is the actual title. That is not something I made up. It's called a goodness of fit test. How well do our observations fit with what we expected to happen? Okay, I like it. So, in this picture, let me see if you guys are cool with this. Do you guys see how, when would chi-square from this? When would this chi-square be 0?
If they were all the same.
If this was perfectly the freaking same, yes? That would be right here, yes?
Yeah.
So, but we know that any sample I pick could have some variability in it. So even if it's not perfectly 0, I can't just stop and say, well, I'm done. No, of course not. So it's always going to be a right tail test. It's always going to be, I've got to be far away from 0, because 0 would mean no difference. I've got to find a sample whose difference is so great that it's evidence the whole population is different. So this is what we're going to find. Here's our alpha. So that's a one tail, so it's all in there. I got to figure out what this chi-square is. This is going to be like my rejection region. Oh, shit. But now it's like, what is our degrees of freedom? And if you think our degrees of freedom is 399, I understand, but you're not right. So here's the difference for this. For a goodness of fit test, the degrees of freedom, oh, you're going to love, this has got so many levels of weirdness to it. Degrees of freedom is equal to the, believe it or not, that K, this K, stands for number of categories. We use K because apparently some math people could not spell categories at one point in the past. That's the drunk history of this. How many categories did we have that we were analyzing? How many categories? What was our data? Doesn't our data fall into categories? Yeah, 5 categories. So what's our degrees of freedom? 5 minus 1, 4. So can somebody please, don't say this out loud yet. 4 degrees of freedom, alpha is 0.05. What's the chi-square for the critical region. You guys get? Yeah. So 0.05, that's out. To the right, all good, 0.05. Go down, stop at 4, so 9.488. And what was it that we got from our sample? We got freaking 5.174. Did we find evidence? And again, now, I really want this to make sense. What did 0 mean again? What would 0 mean? They're all already the same, right? That's obviously not evidence that they're different. So, anything in here, we have not found enough evidence to say that it's different. Anything out here, we have found enough evidence to say that they're different. So can we say that students this semester are doing better than expected? No, we can't. It's different, just not different enough.
So if chi-squared were above 4.8.
Sorry?
If chi-squared were above 9.488.
Yes.
Then we can say yes.
Yes, if that chi-square would have been 11, then we could say, yes, it looks like they're different, and in fact, it looks like they're doing better because it was more passing, less failing, right?
You always have to provide it alpha or assume alpha.
Just like in the hypothesis test, if they don't give it to you, you do just like in the hypothesis test, you assume 0.05 because it's the most commonly used one. I like it. All right, so let me give you this. This one's got, well, okay, we'll go over this example because it's a little different.
At the end of the problem, do we have to like put into words as well?
Yes. So I was just thinking that while I was walking around. So up here I could say, we have not found evidence, sufficient evidence, to say they're doing better. To say this semester students are doing better than previous semesters. Blah, blah, blah. Okay. So you still need a conclusion. I'm not going to be so picky with it, to be honest, but you still have to capture the idea. So look at this example. So up here is an example. I'm kind of happy. I wanted to start with an example where they give you percentages. Because how did we get the expected here? We took the percentage of the total. Of course we did, right? Because that's how many I would expect to be in each category. What's the difference in number 1 up there? What's the expected distribution? It's not a series of percentages. What do they expect the distribution to be in number 1? There's no zero distribution.
Uniform?
Yes, uniform. And what does uniform mean?
They're all the same.
They're all the same. So how did I get 7 in the expected? You see where it says 7, 7, 7. How did I get those 7s?
42 divided by the
Of course. Now, please let that make sense. If the expectation is that they're uniformly distributed, I have to take however many total I've got, 42, and I have to divide it evenly amongst all the categories. So 42 divided by 6 in this case. So it's either going to be percentages, and then I take percentages of the total, or it's going to be uniform, in which case I divide by how many categories, so I uniformly distribute in all the categories. That's the only 2 things that can really happen. Okay, so I work through this blah, 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 blah. So here's the like chi-square star, here's the chi-square called critical, like the rejection region, right? So obviously we didn't make it far enough, so we have not found evidence to reject the claim they're uniformly distributed. You don't have to be all that official in your language. So I want you to try out some of you guys might realize you could use L1, L2, L3 to kind of help you. You don't have to.